Okay, I think we can start again. It's good there are lots of discussions. Okay, I think part of the discussions are also that I wasn't precise enough about what I wanted from foundations at the beginning. Because I didn't want to spend forever on introductions of introduction. And what I want is really a physical picture of the world. And if you care about something more informational, you can be satisfied by answers that I find unsatisfactory. Okay? And that's, in a way, a philosophical disagreement about what we want from physics. And okay, I don't pretend that I have a solution to, or that we can prove who is right or wrong. Okay? I think these informational approaches are very good methodologically, practically, but I have a hard time making sense of them physically. Okay, but I don't want to say more because then I reopen the debate. And so now I want to talk about Bell's theorem. And I know Bell's theorem is very well known to many of you. However, I find it's usually proved in very weird ways that make us have wrong conclusions about it. And so I want to try to present it differently, and maybe this gives you a different intuition about it, or maybe not. Okay, hopefully this is so this is my second big point, and it's going to be Bell's theorem. Why do we care about Bell's theorem? Again, this is in this idea of being as less romantic as possible. And Bell's theorem is pointing to the genuine weirdness of quantum theory. And so certainly one that we have to include in our interpretation, one that we are forced. And so we have to understand it well, okay, exactly what that means. Okay, just a small introduction on Bell's theorem. If you read Bell's paper in Speakable and Unspeakable, it is very clear, I mean, he says it explicitly, that he came up with all this idea of Bell non-locality and everything by studying Bohmian mechanics, by thinking about foundations, and understanding that basically, so he first thought that Copenhagen was the only way, that there was theorems even proving that you cannot add extra variables. And then he said he saw Bohmian mechanics and then saw the impossible being done. Like everything that the theorem said was not possible, Bohmian mechanics was doing. But Bohmian mechanics was extremely non-local in a very peculiar way. And so Bell tried first to construct local versions, and then when he realized it wasn't possible, tried to prove that such local versions were not possible. But in fact, the conclusion is much stronger, and it shows that the non-locality is in a way interpretation independent, even though he guessed it with Bohmian mechanics. So let's start, and I will show Bell's theorem as a sort of game. I'm not exactly going to use CHSH inequalities, even though the inequalities I'm going to show are equivalent to CHSH. So just a warning about that. The first is to do a warm-up. It's often thought to be a trivial warm-up with Einstein, Podolsky, Rosen. Because I feel bad for them, that they are always presented as having been wrong and Bohr right, when in fact it's much more complicated than that. They are mostly right, and at the very end they are wrong. Okay, but they still have a very important argument. So we are going to, again, we're going to gamify things. As you know, Bell's theorem in principle is something that has nothing to do with quantum mechanics. So we can be in a purely game scenario. I will consider, hope I don't mess it up. So I will consider an Alice and Bob setup, which is good. I mean, many people in the room from Alice and Bob. And they are in two galaxies light years away, like super far away. And they are going to be asked, so they are going to be asked questions, three possible questions, A, B, or C. This is where you see I'm a theorist. I kept things too abstract. I should have thought of real questions. Okay. A, B, C. to which they can only answer yes or no. Okay, you can imagine a certain question, I don't know. That's the setup. And the game is very restricted in the EPR case. In the EPR case, you ask always the same questions on both sides. So you ask always A and A, B and B, or C and C. So you ask them the same question always on both sides. And what you observe is that they always answer the same. Okay, this is dangerous what I'm writing. They answer the same, in the sense like for question A, Alice and Bob answer the same thing. For question B, Alice and Bob answer the same thing. So for example, Alice, A, yes, and Bob, A, yes. We do it many times, many times, zillions of times. Every time it's the same thing. Okay. Note that they were allowed to talk beforehand. So before, they were maybe in the center. They could talk. They could establish strategies. But then when we ask these questions far away, they always answer the same thing when asked the same question.
Yeah. It's possible that you ask question A, they both answer yes, and a bit later you ask question A and they both answer
okay,
no.
The real thing would be to restart the whole thing. I would like my randomness to be restarted every time. Or indeed, you could do a list of questions in which case they would be allowed to change. They would be allowed to answer yes to the first A that comes and maybe no to the second A that comes, as long as it's the same Alice and Bob on both sides. Okay. Is that clear? No, not clear.
I'm not sure I understand the setup either. Like, what is this? Like, these are two normal humans?
Two normal humans, maybe they can, at the beginning, they can establish a strategy together or discuss what they will answer.
Okay.
And then they move far away.
Yeah.
And now they will be asked a question. There are two setups that are equivalent. So either I repeat this whole thing, but it's going to be very long many times, or I just tell them, I will ask you a list of questions that you don't yet know, A, B,
you don't know.
Yeah.
And what do you mean by
EPR
case? What does this mean? What do you mean by
EPR? Because it's, okay, then we are going to do Bell, EPR. EPR is the EPR game, but there is no real game here. The only constraint is that they have to answer the same. And that's what we see in practice. We see that they answer the same. And the conclusion from this, because they are light years away, is that they must have decided of a strategy beforehand. Okay? Sort of before the question is asked, they know what they will answer. If you're not convinced by that fact, you have to stop. This is like the crucial part. They are light years away. They will have, if asked the question B, for example, they will have to answer the same. The only way is that they agreed before. Okay? Naively yet. Okay. The only way is that they agreed before. Okay? So Einstein's and okay, they are doing that with photons, blah, blah, blah. But okay, imagine they do it with people. The EPR argument from this is that locality of physics, like nothing can really go faster. No interaction between them can travel faster than light. Locality of physics implies either you say determinism or predetermination of answer. Predetermination. Okay, I'd like to say this conclusion is obviously correct. Okay, so think about it. There is no lie here. This is obvious. If they have no way to influence each other, the only way that they can survive this game, if you like, let's say they die once they answer the wrong thing. Okay, the only way they can survive this game for a million iteration or a billion iteration is if they agree beforehand on the strategy. Okay? And here, strategy is really just fixing the answer or something that's equivalent. They could have a strategy which is, let's look at a star far away. Depending on its fluctuating brightness, we decide the same thing. But still, it's always predetermined before the question is asked. even if only a second before, but it's predetermined. It's like the thing is, yeah. So Bohr, okay, what is the mistake of Einstein, Podolsky, and Rosen then? And why the paper, if you are not, okay, you have to be tolerant, okay, it's written in 1935. Then they conclude, then EPR say, locality is obviously true. And so things are predetermined, like the answers are predetermined.
Can you redefine what you mean by locality?
Like there are no influences of any kind going from Alice to Bob or Bob to Alice that could help them establish a weird way to answer the questions when they know them. You know?
So, yeah, like instantaneous communication.
No, it's not instantaneous communication. I mean, that's the whole subtle thing. It's weaker. Bell will call that local causality. So there is no influence, even influences that would not be information transmitting. We'll see later. I mean, you don't have to. Okay, we are already. I would say, okay, maybe let's zoom out a little bit. If you saw this situation, and let's say they were not light years away, and they started. You would just conclude that they agreed beforehand, or that they saw each other beforehand. Okay.
So, for example, if the question starts with the first 10 letters of the alphabet, you say yes. And this kind of agree. I'm trying to understand what is the rule, or what it. So you're saying they want to play a game.
So far there is no real game. They can talk together, then they move far away. And then you ask them one of the questions, you just notice that they always answer the same. Okay, you're trying to conclude things about what happened in the world that explain this. And I'm saying your conclusions about what happened in the world, since you are asking these two things light years away, is that there was an agreement and that this, actually they knew what they would answer, they knew their strategy before, they didn't make it up after being together. That would be weird. Okay, that would be not possible, just. So this is correct, but then, so this implication, locality, again, this is locality in an intuitive sense at this level, implies that the strategy is predetermined. And EPR say, this is obviously true, and so it means these variables are fixed. Okay, like they are actually extra things we can know. And this, as we will see, is the part that's not correct. But because in fact, this form of locality is not true in our universe. But this part of the argument is correct and is really influential for Bell, and Bell uses it in the theorem, or at least in the second paper he wrote about this. And so then there was a criticism of Bohr, and if you look at it, it's not clear what Bohr disagrees with. So Bohr disagrees with EPR, but it's not clear if he disagrees with this implication, if he disagrees with locality. Honestly, Bohr happens to be correct that the conclusion that things are predetermined is wrong, but not for the right reason. Okay, like he's just saying you're wrong, but okay. So this is, I think, we should give credit. It's not a stupid paper that they understood something. I'm not yet instantiating with quantum mechanics. I will first do Bell's game, and then instantiate that with quantum mechanics. Now let's look at Bell's extension.
I'm sorry, what does Bohr say?
I have no idea, honestly. You read it, it's not clear. I mean, Bell tries to, in the appendix of one of his papers, Bell tries to make sense of what Bohr wrote and concludes, okay, I have no idea what he means. So it's not just me, you know, it seems to be something fairly general that this, especially this critique of the EPR paper is not so good. Okay, what's Bell's extension? It's a very simple extension, and now it's going to be really a game. I'm forcing it to be a game a bit. I'm not saying it's a very interesting game, okay? Now, A, B, C can be different on both sides. They still have to agree when it's the same. When the questions are the same. But you introduce something new, like if you want, this is an optimization problem, this is a constraint, and what they have to optimize is they have to disagree as much as possible. Disagree in the sense of giving the opposite answer. They have to give opposite answers as much as possible. So actually, this formulation of Bell's theorem is due to David Mermin, as far as I understand, the history of this version, who I nastily quoted at the beginning, but this is I think it's a very nice version. Okay, so you understand the rule of the game. You could in principle play it with friends, okay? You're going to be with your friend, then you're going to be separated. You're going to be given a question, A, B, or C. If you happen to be given the same question, you have to agree. You have to be saying yes, and the other says yes. However, if the questions are different, you're going to have to try to disagree as much as possible. So as often as possible to say no when the other says yes, or whatever, okay? And the best would be to really do it once every time and to repeat this whole setup many times, which if you are super far away is kind of annoying, but okay, you could still do it. And so that you can accumulate statistics. Okay, they have to give the opposite answers as much as possible probabilistically. Okay, like they are allowed to have a probabilistic strategy. So this is really not the way Bell phrased it at first, but this is equivalent. Now, because of the constraint, they never know when they are going to be asked the same question, because this is decided in a way when they are super far away. Okay? So because of the constraint, EPR implies, sorry, not EPR, implies EPR argument tells us that they have to fix their answer. They have to agree on their answer beforehand. Okay, because the situations where the questions are the same are a subset. They are going to happen, maybe randomly. And the only way they can never die from if you want, this is an infinite penalty if you violate this constraint. The only way they can never violate it is same as here. They have to agree beforehand what they are going to answer. And so it's very easy to understand that there are only two classes of strategies that are inequivalent. You have three questions. Either they always answer the same thing, either yes to the three questions. You disagree?
Yeah, no,
Yeah. So there are two classes of strategies. And again, we can stop, we'll go slow here because I think that's the heart of the argument. Two classes of strategies. The first is the answer always the same. So for example, A, yes, B, yes, C, yes, on both sides. Okay? Or the opposite, no, 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 okay, it's completely invariant by symmetry. Or they have just one answer different. So for example, A, yes, B, yes, C, no. Okay.
But they don't know the questions.
They don't know what question will be asked, but they have to be ready for whatever will be asked to them because they don't. Okay?
They know that it's either A, B, or C.
They know that it's either A, B, or C?
Yeah.
Ah,
yeah,
okay.
Yeah,
Okay.
yeah. And so I'm saying, okay, of course there are many permutations. It could be just, but I can invert A, B, or C, whatever. They are just labels, and I also can invert the labels of yes or no. But if you were to play this game, really, you would find that this is the only way. Okay, the first is a disaster because you never disagree. Okay, that's the worst one. So we can just look at the second. And then maybe they can probabilistically mix the two strategies, but they can never do better than the first one, than the second one. Okay, so what's the disagreement probability in that case? Well, you want to look, for example, at the probability that Alice has yes and Bob has no. So Alice has yes 2/3 of the time. This is okay, the probability of this. This happens 2/3 of the time for Alice and 1/3 for Bob. Okay, the opposite one is the same. Say 1/3. So this means that P of disagreement, or okay, by disagreement maybe it's like opposite answer. I'm assuming I sample the questions randomly, uniformly, is equals to 4/9. And that's the best. Okay, that's, I cannot disagree more. And this is Bell inequality. Okay, CHSH is equivalent to this. Okay, is it strictly equivalent to this? Okay, for what we want to say, it's equivalent to CHSH. I'm not sure how equivalent it is in general. Okay, so it's a statement. There is no notion of particle or all that. There is no hidden variable. Okay, at least we could reinterpret all this in terms of hidden variables, but it's a game we could do in practice, and we would find 4/9. Okay. Do you agree with this 4/9? So this is important to understand. The advantage of this version of the game, why do we struggle this way, is that the classical bound is really completely trivial to write down. There is no like, I don't know, Cauchy-Schwarz or anything. And this is just straightforward. We can enumerate the strategies. And we see straightforwardly that the best is 4/9. Okay, so now this is not, actually, if they use quantum mechanics, they can do better. Quantum mechanically. Well, what you do is that you consider psi PR, maybe same state. Okay, you could either consider a singlet, but I'm going to consider like this maximally entangled state.
So, Antoine, why did you add this rule of the game that they have to agree when the questions are the same? Can't you just say you want them to disagree as much as possible?
No. This allows me to force the strategies to be fixed.
I mean,
this way I can use EPR's argument as a subcase. That restricts massively the types of strategy. I'm using it for determinism, basically. I'm using this argument to say that they have to fix their answer first. But otherwise, I would have to study all probabilistic strategies.
But here in the sort of metric of the success of the probability of the strategy, you've only quoted the opposite answers, shouldn't you?
Yeah, but that's the constraint. You put a constraint.
Yeah, so this is a hard constraint. Like if you want, they lose, what they have to optimize is how much they disagree under the constraint that they never fail the game, which is like...
Okay, so they don't have the same status. The two first ones
Exactly.
are like the
You're
rules,
right.
and the third is the metric.
I'm sorry, yeah, this is as much as possible, this is the loss function here.
Yeah, okay, thanks. I get it.
And this is
The rule.
This is the rule, yeah.
Yeah.
Okay. And what you measure in that case is pi theta, if you want theta plus, or theta, or just the standard. I give you the complete basis out of. Okay, so you're going to measure 3 various angles, and you associate a question to each of these measurements. And you're going to say A is pi 0, so it's 0. B is 2 pi over 3. And C is... so the angles look on the trigonometric circle. You have... Okay, this is poorly drawn, but these are the 3 angles you consider. Okay, so now Alice and Bob, if you like, they prepare this entangled state, or it is one part of each of one part is sent to each of them. Okay. That at least everyone here understands how practically we could do that. Maybe this is encoded in some polarization state, okay? In principle, that could even be some superconducting qubit, very, very stable in a box, okay? And we send it. And now, before answering the question, they probe the magic box by doing this measurement. And depending on the question, they choose the measurement, okay? So first, we can verify that the rule is okay. Well, this is correct because this state is also equal to 1 over square root 2 Okay, this is the same expression in the rotated basis. So if I measure A and if Alice and Bob do the same measurement, they get their answers are correlated. Okay. So it's clear that this state verifies the constraint. Okay, and this is already present in the EPR paper, although again in completely different ways. Whereas the observables were, I think, position, momentum. Okay. Okay, what happens now if the questions are different? Okay, then this is completely invariant. This is why it was chosen to be very symmetric. So for example, you can assume Bob has A So measures okay, or the opposite, 0 or 1, okay? Then it's projected on 0, and then say, assume Alice measures, say, B. And then you see, using that, and then you see that they give the same answer with proba. So in this subcase, with proba cos square of 2 pi over 3, which is 1/4. Okay, so now how much do they disagree? Okay, what by that I mean the probability of opposite answer it's equal to the probability that they are asked 2 different questions, which is 2/3 of the time, times 1 minus the probability that they agree when this happens, which is 1 minus 1 over 4, and this is 6 over 12, and it's 1/2. And this is strictly larger than 4/9. And so in a way, they can use quantum mechanics to totally respect the rule. So 100% of the time, okay, up to experimental errors, give the same answer when the questions are the same. But they can disagree more than what they could disagree in a world that were perfectly local. Okay? So this is the crazy result in a way. I mean, this is very surprising. I think when we present the game this way, it feels absolutely impossible that this stuff is doable, and yet the result in our world is that. So if you have access to, say, a spin or your spark conducting circuit in the box, you have much more power at this game than you would otherwise do. And yeah, that feels, I think, very surprising. And of course, it was experimentally done, not exactly this way. Okay. And what you get is that px, the experimental probability, is close to 1/2. Okay, I mean, but it's certainly strictly larger than 4/9.
Two variable free or variable free? I'm just confused, like, what happened with the two... Oh, okay.
Maybe I screwed up some time. Okay, so that's weird. So now we can discuss what does it say about the world. Okay, so I'm sorry, trying to be realist about it. So what does it say about the world? And there are basically 2 conclusions that are possible. One that I find is weird, and one that I find is far too weird to even be entertained. So now I'm going to say either Alice and Bob something. What I mean is nature, okay, whatever is doing this. Either Alice and Bob influence each other. And this is non-locality. This is a dominant understanding of Bell's theorem, that this proves there is a form of influence. And the other option, okay, is that they can know a priori which measurement will be done on the other side. Okay, so if they can know a priori every time that on the other side this will be measured, they know when they can disagree or agree. Okay, so this is hard to write. So they know a priori what will be asked on the other side. Why is it weird? In principle, on the other side, you could just decide randomly to do something. Or you could do some weird local experiment, or you could run a random number generator. Somehow they can predict all that. And this is the superdeterminism interpretation, or understanding of this result. What that would mean is that there is a form of determinism on nature that destroys all the appearance we have that we can choose things randomly, all the appearance that we have that actually we choose our measurement settings freely are wrong, and they are everything we do is totally predictable by someone super far away.
I thought there is not like an assumption in the rule of the game that A, B, and C are independent questions, and
yeah, they are sort of sampled randomly. Yeah.
But can you solve, like, at least give an intuitive picture of what's going on quantum mechanically by saying, oh, classically I had a hidden assumption that the answer to question A by Alice will not, but question A and B were independent questions.
Here, I don't think it matters. Like, again, the thing could be, we could say instead that it's a bit more difficult to do the classical argument, but if instead we have said they will be asked a sequence of questions, for example, that would still work. Or maybe you mean what type of correlations do you mean?
I want to but I don't have a good answer about this, but like an image for because the influence each other non-locally is annoying.
Yeah, that's weird. But
so it's about correlation, right? It's like it's
yeah.
knowing that Alice answered P of A knowing B is looks like I'm trying to find a Bayesian explanation.
Yes, but okay, that's why I did the thing first without any reference to quantum mechanics or anything. I think if you saw, let's say they are not space-like separated. You do this experiment with people, and they answer, and the probability of disagreement is 1/2. And you told them you're not allowed to talk during the thing. You would conclude they are cheating, okay? If you do this experiment in practice. You would, without the slightest doubt, conclude that they have cheated. And so in that sense, your natural conclusion before being too intelligent would have been necessarily there is non-locality going on. That's why I think we can be a bit fancy about our definitions of non-locality. And okay, Bell tries to make it precise what he means, and this is his definition of local causality. But I think this is non-local in the most intuitive gut feeling sense of what it means to be non-local, which is that if you saw it happen in practice, you would conclude people are cheating, that they are communicating even though you said they shouldn't during the game. But okay, you will see sometimes people refute the conclusion of non-locality from superdeterminism. There is another way to try to avoid it from the many-world interpretation, which is to say that outcomes don't exist anyway, like all the outcomes happen all the time. And to be honest, I don't really understand in this many-world proof that there is no non-locality, why indeed there is no non-locality. But sort of proponents of many-world claim that it saves them from this type of non-locality. Maybe other remarks about Bell. Otherwise, I wanted to say a few more things about Bell. So certainly, it does not allow faster than light signaling. Okay, so indeed, this is not a communication in the sense that you can send information. The local statistics, basically Alice from doing our local measurements, or Bob from doing his local measurements, cannot do anything, cannot send any information by choosing A, for example. Bob doesn't send information that Alice can see, okay? So indeed, there is no faster than light signaling. Quite interestingly, you might think, okay, but maybe quantum mechanics is the most non-local thing that is not signaling. But maybe you know that's not true. Okay, like there is, you can be more non-local. By more non-local, I mean here doing a better score at the game. Non-local without breaking, without faster than light signaling. And this is the Popescu-Rochlich boxes. I don't know if I want to explain the Popescu-Rochlich boxes.
Just in a few words.
Yeah. So here you can just imagine a box that, so you imagine they have a box. Okay, it's not connected, it's sort of connected with a sort of hidden link like entanglement. You can ask question ABC, ABC. And the box says yes or no randomly on each side, but same, okay, it's sort of a box that's made to win this game, and you understand that but if questions are the same, answers are the same on both sides. Otherwise, opposite. Sorry, I'm a bit quick maybe to. So you can imagine a box where every time, instead of doing this measurement, they press, I don't know, the button A, B, or C on these boxes. When it's A on both sides, it will randomly pick yes or no and make it appear, but it's the same yes on both sides, or same no. And when the questions are different, it's also picked randomly, but they are opposite. Clearly, there is no way to signal with this. You cannot send information by typing A and B. You always get something random. The other guy gets something random. But there is exactly the correlation that is maximal for this game. So they will disagree whenever they can and respect the rule whenever they can. And the Popescu-Rochlich boxes give P of 2/3. And so 2/3 is the max you can do. I mean, our game doesn't have a score better than 2/3. Okay? And clearly, you can get 2/3 without allowing faster than light signaling. However, it's believed Popescu-Rochlich non-locality doesn't exist in our world. But it's something, in principle, you could get higher violations than this, and it's still compatible with relativity.
Doesn't that require faster than light signaling so that they know what question was asked to the other one?
What I'm saying is that
the choice of question also.
Yeah. But if you see Popescu-Rochlich, you're gonna tell me yes, but there is a link between that allows this thing to happen. But this is the same argument for the entangled states. This is exactly the same argument for the entangled state. So the type of non-locality that the PR boxes have is just the same as Bell's non-locality, but stronger. It's just a stronger version. The advantage, for example, I think Gisin, many people now popularize Bell-type non-locality with the PR boxes because they are much easier. Like you can really disagree all the time, agree all the time. Okay. But yeah, another way to say it, in our world, it seems that we will not be able to construct PR boxes that work at space-like separation. The question would have been open for quantum mechanics, and weirdly, we can produce these Bell-type correlations. But say, if you take relativity, introduce the PR boxes in relativity, you introduce no breakdown of anything we know. Okay? There is no grandfather paradox, no bullshit. Like this is totally a world in which there is a small PR box non-localities that we have not yet seen is possible. Okay? People from complexity theory think it's very unlikely because it allows very powerful distributed computation, but I have no idea how hard distributed computation should be. So for me, that's not a very strong argument. I mean, I would have concluded that Bell non-locality is very powerful for cryptographic tasks, and yet it exists. Okay, so it's just maybe this type of non-locality exists. Just to say, you cannot just say that one thing that would have been seducing is if quantum mechanics were exactly at the most non-local before sending signals or something like that. Sadly, that's not true. The PR boxes are better. Okay.
So we should advise Alison Bob to build a Popescu-Roche-based computer.
No, but this actually, these people have thought of this.
Step one.
Sorry, so are there, let's say, more philosophical arguments to select quantum mechanics out of this?
Yeah, there is a whole field of trying to justify why quantum mechanics is natural. It's sort of getting more than classical probability theory, but not too much that you get just the right amount of weird stuff. This is essentially a line that's completely orthogonal to what I'm presenting, which is trying to build a physical theory. And some people are trying to justify the operational principles also from general operational frameworks, say generalized probabilistic theories and so on. I'm honestly a bit less interested by that, but I understand that people are interested in it. Okay. I won't talk about that type of work.
I would think the common point is Occam's razor, like what is, okay. Few
Yeah,
things to say and then we know which to.
One is a sort of operational Occam's razor, one is a more ontological Occam's razor. There were a few things more I wanted to say about Bell, sorry. Okay, you often hear, and this is actually pretty annoying, that it shows that there is no local realism. That somehow combining locality and realism, we get a contradiction. Very, very often, like famous people, famous books. There was no realism business here. I never talked about hidden variable. I never talked about particles. Bell inequality was derived at a very operational level without reference to interpretations or anything. We used it with people in a game. Like there was no notion of realism. So realism can sometimes be referred to the reality of the hidden variable. Here we only use reality of results, okay, of measurement results. That's a very weak thing. So if you want to call that realism, sure. But I'm just saying, sometimes people think that if they drop reality, they can save locality. But since this was never an hypothesis, you can drop it if you like, but that doesn't help, okay? I think that's important to have this logic clear. So there is no mention of realism, no mention of hidden variables. To be fair, the first paper that Bell wrote was explicitly phrased in terms of hidden variables, and he wrote later versions that are more like this, where it's much more clear that this is completely theory independent, and that we are saying something about the world, not so much something about hidden variables. Okay, in the original one, the hidden variables are the strategies. Okay. Sometimes also people say that no determinism is possible. This is proof, you know. Sort of, if you have the assumption of determinism, you reach a contradiction. But that's also wrong, because determinism was not an hypothesis either. Determinism was a consequence of the fact that they have to agree. So determinism is a consequence of EPR in this setup, which then brings the violation. So determinism for us was a consequence of locality. But it was not an hypothesis. So again, dropping determinism alone doesn't save you, okay, because it was a consequence. So it's not an hypothesis. I think it's just many people claim that you can bypass certain things by removing things that are not hypotheses in the derivation. Okay, in popularization, people are super worried about having the audience in front of them think that Bell theorem, Bell type non-locality can be used for faster than light signaling. And since you're a bit panicked about giving this wrong feeling that there will be faster than light signaling, you just revert to something like, oh, but it's just correlations. It's just correlations. And then you can fall into what Bell calls Bertelmann socks. So Bertelmann was a collaborator, or at least, I don't know really a collaborator, but someone at least sharing the same office as Bell. He was always wearing socks of 2 different colors, say one blue, one pink. And of course, if you always one blue, one pink, so if you saw the first sock, you knew the color of the other one. Okay, but there is no mystery in that. This is just the EPR part of the argument, if you like, the deterministic part. But Bertelmann socks, like we cannot explain the weirdness in this scenario just this way, as something hidden that we didn't know, that we just discover after. So this is not just having an information hidden and that we just discover it, and so it materializes on both sides, but it was there all the time. Precisely, the argument of Bell is to show that EPR correlation cannot be explained in a Bertelmann-Sachs type of way. Okay, so earlier this year I was in Vienna, and Bertelmann himself recalled this argument of Bell, and at the end he showed his socks, and they were indeed opposite colors. Another thing I think that's important is that also sometimes people say no local hidden variable theory is possible. And this can be interpreted in 2 ways, which in French are written in inequivalent ways, fortunately for us. And the question is how you, in French, do you put an S or not? So do you say théorie à variable cachée locale? So is the local basically referring to the hidden variable or to the theory? Okay. Well, the hidden variable is in Bohmian mechanics. Okay, and then you say this, you're like, there are no local hidden variable theory, so it means everything, so it means the hidden variables have to be non-local. Okay, I abandon this, I go back to Copenhagen, okay? But Bohmian mechanics has completely local hidden variables, okay? So the local here refers to theory, like the dynamics has to be non-local. And I think it's a much less weird thing. And if you see it in French, of course, people always act as if the local refers to the hidden variables, which is again not true, not what Bell proved. Okay, so I did all the wrong interpretations of Bell's theorem. I think at the end, it's something we have to live with. Okay, Bell's theorem. And all interpretations that you will have to construct, all physical theories of the world that you will construct, will have to have some form of non-locality, and that's unavoidable. And so when you see, this is to prepare you, when you see later that some theory we are going to propose, again, not necessarily because we believe in them, but just to show examples, that they are non-local, you should not see it as a negative thing. You should see it as a positive, because if it were not so, it wouldn't violate the Bell inequality. Okay? So non-locality is the fact of the world, okay, unless you have superdeterministic theories that I'm sort of excluding here. Some people are proposing toy examples of superdeterministic theories. I don't find them super believable, like even less believable than the other ones. But yeah, so now interpretations have to live with what we did. What I was thinking was to do interpretations next time. I can still start with collapse models, but maybe that's how's the crowd feeling? Maybe that's a lot. No, I don't know. Do you want to start collapse models? Okay, people are confused. I think maybe it's going to be clearer if I do collapse models next time, perhaps, and then Bohmian mechanics the time even after. And that we stop here with sort of the generalities about.
Are you going to also tell us about why? Because, for example, you talked about the solutions for the measurement problem.
Yeah.
And so one of the solutions was like he was telling you to add, for example, to change the second postulate to something like.
Yeah, that's collapse models. Yeah, that's a collapse model. So indeed, so there are two strategies. Okay, change two or add extra variables, and I will present both. They are the most immediate. Then you have much more complicated things, but the ones that have convincing, that have given complete stories about how this would work. These complete stories can be disliked, but the advantage is that they are clear stories that you can say what they say. And so they are the ones that I will present, but they are, I think the other ones are at levels of development that are much lower and as a result don't warrant much discussion. I might briefly mention the operational ones to be fair. The problem is that if I start explaining cubism or relational quantum mechanics, I'm sort of unable to explain them in a neutral way. I sort of disagree too much, and I can't even make the basic case for them. So I will mostly present the realist one where at least I understand the motivation better.
I'm always confused by the notion of locality, because I think maybe you can clarify this. There's the notion of local laws of physics, like the equations of motion depends on your derivatives and so on. But then with entangled state, there's a notion that states are delocalized.
Yeah.
What is it meant when we say local theory? Is it one or the other or both?
Yeah. You mean in reference to this?
Yeah.
What does that mean?
Yeah, because I think so.
For example, Newton's law with the 1/x potential is a non-local dynamical theory.
What?
Is a non-local dynamical theory. In the pure potential case, you have action at a distance, but points are local. In Newton's original theory of gravitation, he says it actually complains that there is a weird action at a distance. Before you introduce mediators, say gravitons or whatever, this is a non-local dynamics, but of purely local variables. Like the positions are sharp, they are not spread. That'd be sort of the opposite of what you said. That would be an example for me of a theory that has totally local variables, but the dynamics is not. Okay, Newton's law. I mean, you can say it's mild, it's decreasing. And what's weird with entanglement is that it doesn't decay with distance. It sort of creates a bond that seems not decaying.
When we say non-locality in the sense, so an entangled state is delocalized, can we say it's non-local? Is the right word, or is this a contradiction?
I mean, here.
Entangled state is non-local.
Okay, this non-locality is about sort of something that you declare is the real thing in your theory, and then you wonder if it obeys local equations or not.
What's the definition of the local theory? Yeah, that's the question.
Yeah, you have local equations of motion, say. Maybe you even have a light cone, but since we are doing non-relativistic...
Local equations of motion, meaning?
Okay, in quantum mechanics, the dynamics of quantum field theory is local at the quantum state level. Of course, what brings Bell inequality is that the collapse then is something that acts on on a space-like hypersurface instantly. Okay, and if you assume, for example, that there is a delay in the collapse or something like that, you don't recover Bell's inequality. Okay, so there is even though the dynamics at the state vector level looks very local, we get some non-locality in the predictions thanks to collapse. And that's why many world people will claim since we have no collapse, everything is local, and there is just a split of the wave function that reproduces the right probabilities. But all of that happens locally. The price to pay, of course, is you have to keep the branches. But another way to say it, the price to kill the branches and get only one branch stochastically, this is a non-local operation. Like, there is no way otherwise. Okay, very good. I don't know if there are other questions. Otherwise, I think it's a good point to stop.
Basically, you're saying the no existence of no. Basically, this is also a way to say that if there is no local theory of hidden variables, then necessarily you need to add something to postulate 1 and 2. That's somehow you would.
No, so here, so what you're trying to disprove in a way is that there are extra variables maybe that explain all measurements on top of the wave function. And if such variables exist, they have to interact. By knowing these variables on Alice's side, you don't have enough to predict what she will measure. You need to know them together, model the measurements on both sides, and see that this complicated evolution will bring a violation of Bayes inequality. But you will need non-locality in the evolution. That would be very obvious in Bohmian mechanics, where this is precisely what happens. So there are local variables on each side, clearly, that if you want even a bunch of local variables, but they obey a completely, there is a non-local dynamics that when you measure sends the particle one way, the other way, corresponding to measurement results. But to get the right statistics, really, you require this interaction at a distance. So in some of these reconstructions, you explicitly have interactions at a distance that don't decay, that are meant to, that enable this violation.